Solar farms as Rainmakers, a geoclimate paradox. The UAE's large-scale photovoltaic installations could inadvertently induce localized precipitation, blurring the line between renewable energy deployment and active climate intervention. A recent modeling study suggests that solar panel-covered artificial black surfaces exceeding approximately 20 square kilometers generate sufficient additional heating to strengthen updrafts and, under favorable atmospheric conditions, promote localized rainfall.
This finding introduces an urgent strategic tension. The very infrastructure designed to mitigate global carbon emissions may now be implicated in regional hydrological modification. For the UAE, a nation already investing heavily in cloud seeding and desalination, the prospect of unintentional rainmaking from solar farms presents both an opportunity to enhance water security and a risk of disrupting existing weather patterns.
The initial situation thus demands careful evaluation of the urban heat island effect transposed to desert environments where albedo contrasts are extreme.
The albedo shift and atmospheric forcing swapping reflective desert sand for dark photovoltaic arrays fundamentally alters the energy balance, creating a thermal trigger whose significance scales with array size. The status quo in the UAE's solar strategy embodied by projects like the Mohammed bin Rashid Al Maktoum Solar Park relies on vast tracts of black panels that absorb far more solar radiation than the surrounding sand.
Underlying this shift is a straightforward thermodynamic principle. Lower albedo surfaces heat the lower atmosphere more intensely, driving stronger thermals. When a solar farm exceeds the critical threshold of 20 square kilometers, these thermals can penetrate the planetary boundary layer and, if sufficient moisture is advected from the Arabian Sea or Persian Gulf, trigger convective cloud formation.
The so what lies in the fact that this effect is neither designed nor controllable, introducing an unpredictable variable into regional climate models and water resource planning. Such inadvertent geoengineering underscores the need for integrated land use and climate impact assessments before expanding desert solar infrastructure.
Thermodynamics of artificial black surfaces. The mechanics involve concentrated heating, enhanced convective available potential energy cape, and moisture convergence at the mesoscale. In-depth analysis reveals that a 20 square kilometers solar array can raise local surface temperatures by 3.5 degrees C relative to ambient desert, creating a persistent thermal low that draws in surrounding air.
This convergence lifts moisture-laden air parcels to the lifting condensation level, and when CAPE exceeds 500 J/kg, cumulonimbus development becomes probable. The key players here are the radiative properties of the panels themselves. Most commercial PV modules have an albedo of 0.05–0.10 compared to desert sand at 0.35–0.45, and the absence of evaporative cooling that would occur over vegetated surfaces.
Simultaneously, the smooth non-porous panel surfaces reduce the bone ratio, funneling more energy into sensible heat rather than latent heat. Complex feedback loops then emerged. Increased cloud cover could reduce solar farm efficiency, while precipitation might wash dust off panels, both altering the very forcing that initiated the rain.
Unintended consequences and strategic leverage. The UAE now faces a dual imperative: harness this effect for managed water security while guarding against cascading ecological and geopolitical risks. Looking forward, the most probable outcome is that solar farms in the UAE will induce localized rainfall during the monsoon transition months June–September, offering a supplementary water source for agriculture and aquifer recharge.
However, the risk of triggering or amplifying flash floods in wadis worsened by the impervious surfaces of the panels themselves cannot be ignored. Strategically, the UAE could position itself as a pioneer of opportunistic radiative management, intentionally designing solar farm layouts with gaps or variable tilt angles to modulate convective intensity.
Yet such actions would invite scrutiny under the nascent governance frameworks for solar radiation management (SRM), as the effects may be transboundary if moisture streams are altered. The final verdict is that solar farms have become inadvertent climate manipulators. The path forward demands a delicate balance between optimizing energy yield and responsibly managing an emergent form of regional weather modification.